started about a minute early, so we're just waiting to see who, if anyone, shows up. Okay, so people are starting to file in. Let's wait just a few minutes, and we'll start. I'm Charles Clark. With me in the audience today, Professor Michael live here, I mean, Professor Michael Copeland of the University of Maryland, Professor Guido Popillo of Strasbourg University in France, Yishi Wang, a graduate student at the University of Maryland in the chemical physics program here. I'm Charles Clark. Let's see, all the viewers have disappeared by now, so we're just going to proceed anyway. I thought I'd offer a chance for students in the Coursera class to get together online. And if you're just joining, could you mute yourself, please? Mr. Anupam, would you please mute yourself?
Okay.
I'm Charles Clark.
Okay, would anyone who's on, would you please press the mute button so that we don't get an interference? I don't know how I can do this. There, we've done that. Okay, so I thought I'd start just by going through one of the lectures from week 7 that has already been published, get some comments from people on the audience. It's one of my favorite subjects: gauge potentials, magnetism, and spin. So I'm just going to walk through it. These are for those of you in the audience. I know you haven't looked at these things. These are lectures that run between 8 and 15 minutes. There are either 4 or 5 parts in this one. I forget how many. And so I'll go through slightly slower pace than I might do in the video, but just use the same materials. Okay, so heretofar in the course, we've been dealing mostly with the Schrödinger potential equation, with which you're all familiar. Psi is a wave function. Its time evolution is given by this operator. P is the kinetic energy operator. That's traditionally represented as gradient with respect to R, and then there's a potential. So this equation is defined in terms of potentials, and as you see, the potential satisfies this equation where F is the force. So it's a first-order differential equation, which means it's undetermined. It's undetermined uniquely. It has, in particular, an arbitrary constant. So is that a feature or a bug? Now, there's a standard thing within the Coursera videos to have these in-video quizzes, and this is the one that was given. I don't know if you can see it on the screen, but basically it says, is that legible? Can you see that? Well, it says if you have one potential, V of R, and you create a new potential which adds a constant to it, and it just says this is something you could do by carrying the apparatus up to the higher floor in the building, if gravity is in effect. That just changes the baseline. It's a real physical thing you can do. And it asks the students to give the dimensional units of that constant on multiple choice. Seems simple, doesn't it? Changing the potential by an overall constant value is not just a mathematical gimmick, it's physically feasible. If you move the thing up, you change the constant of potential due to the gravitational attraction. And now this is another in-video quiz which asks the student to identify how the wave function changes in time when the potential is changed by a constant, and you know how that's done. So if V naught is the constant, so if you have an original potential V and a wave function psi, then if you add V0 to U, then the new wave function is just the original wave function psi times an overall constant. It's not observable in itself, but it's very helpful to keep this in mind when thinking about certain types of interferometry. Here's an example from neutron interferometry, another one of my favorite topics. And in this neutron interferometer, there are two paths. A neutron is incident here, and the beam is split at mirror A. At this point, this path is reflected back to this mirror D. This path is also reflected at point D. They're recombined by a beam splitter, and then the output ports are monitored. And you get an interference signal. And as implemented by Colella, Overhauser, and Werner, the famous experiment, one of these paths was higher up in the gravitational field than the other, so there was a phase shift. It was the first measurement of the effects of gravity on a quantum particle. Okay, so, but the subject of this lecture is gauge potentials. So these are a form of potential of much richer definition than, let's say, this traditional scalar potential. Here's the acceleration due to gravity, and so GZ, the gradient of GZ. So you get the classical force equation is Newton's law, constant acceleration. The simplest gauge potential, and actually the only one we're going to discuss during this lecture, it's the most important one, is magnetism, and it has a vector potential A, which satisfies this differential equation. So in other words, A is a vector field, the curl of which gives the observed magnetic field. And it's the magnetic field, yes, here you see below, the magnetic field is the actual observable quantity. Just like the potential is not really observable in an absolute sense, neither is the vector potential. And so the equation of motion, the Lorentz equation of motion in Gaussian units, is just force is equal to the proportion of the cross product of the velocity and the magnetic field. So this means that the vector potential is very non-unique, if that's an adjective that gets degrees of qualification, because you see, if you have two vector potentials that give the same magnetic field, then they're related. If you pause and consider this identity, then it turns out that A1 is just A2 plus the gradient of a function, where f can be any function. So if you have one vector potential, you can compose an infinite number of others just by choosing some arbitrary function and taking its gradient. It's a much, much stranger, almost mysterious generalization of this constant. Now, okay, so this is one of these in-video quizzes that invites the student to choose a vector to identify a vector potential that gives the magnetic field in this room, in this very room. In this very room, with the Earth has a magnetic field, we can take it to be a constant. We can take it to point along. We'll call this the z-axis or the north axis. And so the exercise says, please find a vector potential that defines that function. And there's a couple of simple choices. Basically, the choices are linear functions of the spatial coordinates. Several components are linear functions of the spatial coordinates. I'm sorry these things don't show up so well on the screen, but you shouldn't be sorry, because otherwise I'd make you answer those questions. Or no, it would be my polite request. It would be my polite request. It would be in your best interest to answer those questions. Okay, so now those who are joining the broadcast, could you please mute yourselves? Thank you. So now, how do we use the vector potential in actually solving problems? Well, I'm just going to cite this. This is a well-known result. It's obtained from classical mechanics, where you get a classical Hamiltonian, and then to go to quantum mechanics, you replace the classical particles by classical fields by operators. And so there's this principle of minimal substitution that says when you have a particle of mass m and charge q, and you have a Hamiltonian with no magnetic field, then when you turn on with the Hamiltonian with the magnetic field, what you do is you replace the momentum operator by this. The momentum operator minus q over c proportional to the vector potential whenever the momentum is encountered in the Hamiltonian. So for the simple case of a charged particle, a free charged particle, the Hamiltonian is p squared over 2m, and now by the minimal substitution, you get this Hamiltonian. This has amazing consequences. Lots of things change. So first of all, let's consider the velocity operator. The velocity, you can convince yourself, the velocity is just the derivative of the Hamiltonian. Classically, it's the derivative of the Hamiltonian with respect to the momentum. And so now the velocity contains the momentum and the vector potential that you chose, which is totally arbitrary. I mean, how can that be? How can that possibly be? Well, if you think about the momentum operator as a gradient, you can see how that works out. And amazingly, the different Cartesian components of the velocity operator no longer commute with each other. So for no magnetic field, the velocity operator is just p over m, and the components of px, py, and pz that all commute with each other. You turn on the magnetic field, the velocities no longer commute. And here's the expression, but I like to write it this way to show how quantum and how magnetic it is. V cross V is an imaginary number times something that's proportional to h bar times something that is proportional to the local value of the magnetic field. This is about as quantum and magnetic as it gets. First of all, it's a cross product of a vector with itself. This vanishes. This one is imaginary, and then it's proportional to Planck's constant, so it goes to 0 in the limit that h bar goes to 0. That's the classical limit, as it ought to, and it goes to 0 as the magnetic field goes to 0. There's a lot in this equation. In fact, as I'll show you, this is like the explanation of everything. Then the Hamiltonian, let's see, let's just go back. Here's the Hamiltonian. You see, this is v squared. So the Hamiltonian can be written as 1/2 mv squared. Sound familiar? So in the next part, we'll look at the consequences of this. Okay, so I don't know how long that took. It took me less than 14 minutes to get through that. In the video was probably something like the same, like the time. So here's part 2, a little bit longer. This begins with the discussion of magnetism in classical mechanics, and it starts with this amazing theorem that was proven. Actually, it was first proven in Niels Bohr's thesis, but apparently nobody could understand it. And then this Dr. van Leuven, who worked at either Delft or Utrecht, I forget which, a Dutch university, in her PhD thesis proved that all magnetic properties that were known, magnetic properties of material, were completely inconsistent with classical mechanics supplemented by statistical mechanics. So the statistical mechanical theory of matter, which had been so successful in predicting thermal properties and all these things, a wonderfully successful theory, could not possibly describe magnetism at all. I'm going to go see why that is in a moment. So this was, and here's a paper. It's available in supplementary materials in the course, Problems with Electronic Theory of Magnetism. So it takes the classical theory of electrons as developed by Lorentz and shows that it cannot possibly give rise to magnetic properties. So actually we're going to go through a semi-proof of this theorem, and maybe it's more like a mnemonic device than a proof. But it's like once you know something exists and you have some way of thinking about it, you can usually make more progress than if you don't know. So here's the mnemonic device. The force on a magnetic field by the Lorentz equation is the cross product of the velocity. Is proportional to the cross product of the velocity. Well, now I hope you can see that from this equation here, if we take the scalar product of r dot on this, which is r dot dot. Sorry for saying dot all the time, but I think you know what I mean. Then that's 0 because the velocity, scalar product of velocity with the velocity cross b is necessarily 0. And so that says that the kinetic energy of the particles doesn't change. Or another way of thinking about it is the force is at right angles to the velocity, so the magnetic field never does any work on the particle. It deflects the orbit, but it doesn't change its energy. So in other words, the energy of a particle isn't changed by the presence. If you have a particle and you turn on a magnetic field, the energy isn't going to change. Oops. Okay, so this can the consequence of this can be formalized by going to the classical, calculating the classical partition function. Now, nothing is a prerequisite for taking this course, including statistical mechanics. But statistical mechanics won't kill you, even though they say it killed Boltzmann and Ehrenfest. You may escape, and it's based on this partition function, which is a measure. It's something that counts all the states of the system, and then from various operations on the partition function, we can calculate the response of matter to various external influences. So we're going to calculate the partition function, which is just integral over the coordinate and the momentum. We'll do it for a single particle of the e to the minus h over kt, where h is the classical Hamiltonian. And note that because of the presence of h cubed in the denominator here, the partition function is a pure number, has no dimensions, and that number is the number of thermally accessible states of the system. Okay, so now in zero magnetic field, we'll just talk about this Hamiltonian. There's some overall potential and there's kinetic energy. And now I hope you can see that this partition function factors into two parts, one of which is determined only by the spatial coordinate, and one of which is due to the momentum coordinate. And this part is independent of the potential. So you need to calculate this only once in your life, and then you can use it for every problem with statistical mechanics. So what follows now is a little inside joke. I've been tormenting the poor students by asking them to do Gaussian integrals over and over and over. And I'll stop asking when people can just tell me what's the answer. You know, if you're going to be a physicist, you need to be able to just state the value of this integral. And it's been used a lot in these variational exercises of quantum mechanics that I was using early in the course. But here it is encountered in statistical mechanics. It's a Gaussian integral. So this is just like you can write as the cube. You can write as the cube a product of three one-dimensional integrals, and that cube is something like 2 pi mkt so the individual integrals are 2 pi mkt to the 1/2, and this one is the product is 2 pi mkt to the 3/2. Okay, so now here's the core proof of Dr. van Leuven. When you put in a magnetic field, how do you put a magnetic field? You use the minimal substitution. So the partition function, it affects the momentum space part of the integral, and you're left with this. Now, who has an idea how to evaluate this? I mean, look, it helps to have done it before. And this is just so P is the independent variable here, do you see? A is a vector valued function of position. Sounds impossible, but it's trivial, isn't it? Isn't it trivial? Exactly. Professor Papillo made the prescient observation that this is just like some vector, right? And so it's just a shift of the origin of the integration. So in other words, this integral is completely independent of the vector potential. It doesn't matter what it is. It vanishes. So the partition function does not depend upon the magnetic field. And so something like the magnetic susceptibility of a material system is the second derivative of the partition function with respect to the magnetic field strength. It's 0. There's no magnetism, okay? Despite the fact that you've got thousands of magnets in your automobile and that ships have been using compasses for thousands of years, magnetism's impossible. That's a surprise. It certainly caused a lot of controversy. So there's a rich literature of at the time, in the late, about 100 years ago, people trying to pick apart, find the loophole in van Leuven's theorem. Take it from me, there ain't one. Magnetism is purely a quantum effect, as we'll now see. Okay, why does quantum mechanics make a difference? Well, let me just say, right, that here's something we are able to do in classical mechanics because position and momenta commute. So we can take out the momentum space part, and we can do that universally once and for all time. Then, fool around with the position as needed. In quantum mechanics, you have, well, things don't separate like that. the exponential of a sum is not the product of an exponential if the parts of the sum don't commute. And actually, in quantum mechanics, there's a different way of writing this, but it's more or less in agreement with the classical prescription, except for this non-factorability. And so this non-commutivity of the several parts of the Hamiltonian was something that we saw in the last part. Here's this cross product of the velocity operator with itself. Here's the here's the kinetic energy operator. So as we're going to see now, well, in classical mechanics, for example, the Hamiltonian can be 0. Just have a particle at rest, or you can choose a constant where the Hamiltonian function can be 0. In quantum mechanics, as we'll see, in fact, you've seen this before. If you've taken quantum mechanics, you've seen something like this before. It means, okay, so let's say classically we can have v dot v. V can be 0. Quantum mechanically, the components of v don't commute, so we can't have a vector length 0. The uncertainty principle prevents it. That's exactly what this says. And so Landau used this fact when he's 22 years old. He wrote a paper that explained the phenomena of diamagnetism of metals. And so we'll now solve the Schrödinger equation more or less the same way Landau did. Not exactly, but it's close enough. So in my opinion, once you've seen it and understood the basic principle, which is that the commutation relationship that you've shown implies the uncertainty principle, and then that can be picked apart to generate raising and lowering operators. Once you've understood that, you should be able to reproduce it, but I'll walk through the steps as simply as I can. So here's the commutation relation. Well, we first say we're going to treat the problem of a uniform magnetic field. I mean, things aren't going to get if we can't solve that, it doesn't get simpler when we have a very complicated field. So we just choose the field to be along the b-axis. Then, dig it. The velocity operator v3, which is the velocity along the magnetic field, commutes with the other two velocity operators. Do you see that? Because, in other words, if I take v3 in here, if I have one of these as v3 and the other is v1 or v2, then what's here on the right-hand side is the component of b along any axis other than the z-axis, so it's 0. And this, look, this is what you know from classical mechanics. If you have a magnetic field and a charged particle, the charged particle travels freely along the direction of the field. The force is at right angles to the field. So this constancy of v3 is consistent with the classical picture. Okay, so now we're left with just one commutator, v1 and v2, and then I've written it this way. Does this look familiar, h bar omega? It does to me. Omega is often called the cyclotron frequency. So v1 and v2, the commutator is I h bar omega over m. Okay, well now wait a minute. You've seen before commutators that are proportional to I. Here's one. I mean, this is the foundation of the Schrödinger equation, the commutator of x and p, if I've done it right here. Yeah, plus I h bar. So you see, this is just the commutator of conjugate variables. Okay, that's like bragging, sounds like. Let's just create let's just synthesize the variables. So The next step is I make an operator, which is like this. It's, again, you know that when you have the, first of all, the Hamiltonian is quadratic in V1 and V2, and then V1 and V2 have a commutator that's imaginary. So that means it's a harmonic oscillator. It's just like X and P. When you have a quadratic Hamiltonian, you know, for harmonic oscillator, you have, instead of V, this is V1 squared plus V2 squared. For harmonic oscillator, it's P squared plus X squared. So there's A. Then A dagger is just the V is self-adjoint. That's easy. You know, you should show that, but it's easy to show. So A dagger is just V1 minus I V2. Then you can calculate A dagger A is equal to -1 just using the defining variables. So, you know, like that's it. To summarize, one last step, or maybe two. We got these raising and lowering operators. Okay, let's calculate the product A dagger A. And so when one does that, you see you get back something that's proportional to the Hamiltonian here, plus a constant offset. And so it turns out the Hamiltonian can be written like this. It is the Hamiltonian of a one-dimensional harmonic oscillator with energy h bar omega and 0-point energy h bar omega 2, and then the free motion along the b direction. And that's why you have diamagnetism. There's a turn on a magnetic field and you get a 0-point motion of ensemble of charged particles. And that I show this, made a little video of diamagnetism in action, levitation of a chip of pyrolytic graphite on a magnet. You can find a link to that in the class website. I think now might be a good time for me to shut up and see if anyone is still tuned in. Let's get the make the screen share go away. Any comments or questions from anyone? Feel free to unmute yourself if you'd like to ask a question. Okay, if not, we'll do one more of the third of 5 parts, and then you know, maybe we'll have a discussion in the room or something. I don't know. Where was I? Oh, so this so diamagnetism is a universal effect in materials. It's purely repulsive. It's much less important than the other, in my opinion, much less important than the other forms of magnetism, ferromagnetism and paramagnetism, which are even more quantum than diamagnetism in the fact that they derive from electron spin. What's electron spin? That's sort of the subject of the next part, which you might say it's kind of a derivation of spin from the Dirac equation, which is, like, in my opinion, the simplest and most beautiful equation in physics, and it's the one that delivers. This is Latin for the biggest bang for the buck. So Dirac, at the age of whatever, 25 or 26, sat down and with the goal of reconciling special relativity with quantum mechanics. You can kind of see what the problem is. Here's the Schrödinger equation for a free particle. Actually, what we're going to do now, we're just going to talk about the Dirac equation for a free particle in one dimension. Like, what could possibly go wrong? So here's the Dirac equation for a free particle, and so the P is a gradient of the momentum is represented as a gradient. So this is first order in time and second order in space. And so that's not relativistically invariant. And Dirac said it's kind of unsatisfactory. We ought to find a relativistically invariant theory in which is both first order and time and space variables, because we can interchange them arbitrarily by choice of reference frame. And so he also explains most beautifully in his book why the Schrödinger equation must be first order in time. Why it can't be like the traditional wave function, which is like d squared dx squared minus 1 over c squared d squared dt squared as an evolution equation. Dirac said it is absolutely necessary that the generalized Schrödinger equation be first order in time. And that's because quantum mechanics says that that's a superposition principle. The system is described at any given time by its state and not by the rate of changes of state. The wave function at a given time contains all information that we can extract from the system. And so the evolution equation has to relate the state at a slightly later time to the state at the previous time. So if you think about it, you take that time interval to 0, you get something that psi of t plus tau is psi of t plus something times d psi dt, and that's the operator that advances you in time has to be a unitary operator to preserve the norm. That's why you need a first order in time equation. So what do we got for a free particle? Well, we've got the momentum, we've got the mass, the speed of light, like E equals mc squared. And so Dirac said, let's try to find an equation which will, of this form, so it's first order in time and in space. If we require the free particle to satisfy Einstein's relativistic relationship between energy, momentum, and mass, we have to have this. And that means that alpha squared, when you do it, alpha squared and beta squared are 1. You just like square this thing, okay? So you get alpha squared c squared p squared, and then a beta squared m squared c to the 4th, okay? That means alpha squared and beta squared have to be 1. And then when the cross terms from this contain not a commutator, but an anti-commutator. And so you need this anti-commutator to vanish. And you know what? That's all there is. That's almost all there is to the Dirac equation. Because it doesn't say what alpha and beta are, because we don't actually know. There's an infinite number of choices. They're all equivalent. Let's see, what was my next in-video quiz? Oh, yeah, the in-video quiz it gave a choice of, for the one-dimensional Dirac equation, let's find an alpha and a beta. So they can't be numbers because numbers commute. You've got to have things that anti-commute. They must minimally be a two-dimensional object if we're going to give them a numerical representation. And so you can choose. Here I've chosen. I'm sorry if you can't see this. One correct choice is alpha is the conventional sigma x, where sigma x is a Pauli matrix, and beta is the conventional sigma z. Another equally correct choice is that alpha is the conventional sigma y, and beta is the there's a misprint, darn it. Beta is the conventional sigma x. Okay, so actually, maybe where did these non-commuting numbers come from? Well, you actually have a lot of familiarity with non-commuting operations in daily life. Rotations are one of them. Rotations and reflections. So here's sigma x, which is a reflection. In if you look at its operation of vector, it's a reflection in a line of 45 degrees. Sigma z or sigma 3 is just the inversion of one coordinate. And so when you do these operations in sequence, the end result depends upon the order of the sequence. Okay, so we get this equation, and then we can find solutions that are plane waves or free particle. And as an exercise later, I ask people to show that if you have a solution of positive energy, you can construct from it a solution of negative energy. And it's the solutions of negative energy are indistinguishable in terms of boundary conditions, everything from the solutions of positive energy. They're perfectly acceptable, and they indicate the existence of antimatter. Okay, so now one last remark in this part. The Dirac equation for a free particle in 3 dimensions. So this is just the natural generalization. We want something that's a linear function of both space and time coordinates. And we have, so we're going to look, just find the conditions that must be satisfied by, so now instead of just having 1 alpha, we have 2 more, we still have a beta. And so the relativistic dispersion relation is honored if the anti-commuters, if alpha j and alpha k anti-commute, and they anti-commute with beta. So commutators don't appear at all in the Dirac theory. And now, quite an astonishing thing that is mentioned in Dirac's paper, copy which was made available to the students in the course. The angular momentum operator, orbital angular momentum, doesn't commute with h. So it's like the orbital angular momentum of a free particle is not a constant of the motion. I mean, if I had discovered this instead of Dirac, I would have said, to hell with it. If the angular momentum isn't conserved, I don't want any more, because that doesn't work. But what we'll see, the proof is straightforward, okay? You just put this, just do the commutator, because all you've got here is P, and basically, in exercise that people did previously, they learned that if you have any vector and you take the commutator of the angular momentum with that vector, what you get is a rotated vector. So that's manifestly not zero. I think this is inline quiz says that. Okay, well, I'm actually going to be very briefly go to the next thing, because it turns out that here is the commutator of the angular momentum with the Hamiltonian. It's not zero. This turns out to be a feature rather than a bug. So I mean, here's L and H. Now look at this. We've got an imaginary number and then a cross product of these operators alpha, whatever they may be, with the momenta. And now, what next? So, as was done in some earlier lectures in the course, when you find something doesn't commute, but it has a relatively simple form, it's prudent to look at other objects that you can make by simple products of things that exist in the description of the equation, and see if they generate other terms that can be used of the same type. So let's try to identify some constants of motion that are based on quadratic forms, and completely anticipating the result. I'd say let's look at the quadratic form alpha cross alpha, which is alpha 1, alpha 2. For example, alpha 1, alpha 2 minus alpha 2, alpha 1. And I've defined this S just in terms of that because I know I found in making this assumption that this is a preferable form for reasons you'll see. So let's see. Here we are. Here's the Dirac equation, 3 dimensions again. These are just the basic. These are the definitions: the Hamiltonian, the angular momentum, and then with the results we get that say that give the anti-commutation relations. Here's this commutator of L with H. And now it's candidate quadratic form. So I'm not going to go through this in detail, but there's an important thing here which shows you that even though the Dirac equation doesn't make any statement about commutators between the alpha and the beta, it turns out that commutators of products are implied by the anti-commutators of the basic quantities. So here's S1. It's just alpha 2, alpha 3 minus alpha 3, alpha 2. Well, this is just proportional to alpha 2, alpha 3 because we have the anti-commutator. So now what's the commutator of this with beta? Well, it's just this. It's alpha 2, alpha 3 beta minus beta alpha 2, alpha 3. But now do you see, because we have the anti-commutator with beta for any alpha, we can pass the beta past this one with a minus sign, introducing a minus sign from the anti-commutator. Then we can pass it again to the other side, get another minus sign. So S1 commutes with beta. What about the rest? What about S1? Does that commute with alpha 1? Well, once again, it's the same idea. We just construct the commutator, and we see we can pass the alpha 1 through with a couple of sign changes and get 0. And then now here's the other thing. S1 alpha 2. Now you see something that looks more familiar. Once again, a very straightforward operation just based on the anti-commutator relationship, not on the commutator, which is never given to us by Dirac. And you see the commutator S1 alpha 2 IH bar alpha 3. That looks like an angular momentum commutation relationship. And anyway, what happens when you take this vector S that I've defined in terms of the cross product of the alphas and commute with the Hamiltonian? You can show, it's just doing the same things that I've just done here, that the commutator of S and H is minus IH bar C alpha cross P. So it's minus the commutator of L with H. So in fact, this vector, J, L plus S, commutes with the Hamiltonian. And let's just make it very clear. In the limit H bar goes to 0, S goes to 0. It's purely a quantum mechanical quantity. It's based on these complex numbers, anti-commuting pure numbers of Dirac, so it's an intrinsic property of the Dirac particle. And it turns out that when you calculate this product S dot S, it's just equal to 3/4 H bar squared, which is H bar squared times 1/2 plus 3/2. So that means that you get a spin of a half. So all this comes from what you might say is the sort of simplest, most straightforward equation imaginable. You get the electron spin, you get antimatter. I mean, that's kind of an exercise to be shown later. It turns out that the electron magnetic moment, as predicted by the Dirac theory, is in agreement with experiment, and it's completely non-classical. It's off by a factor of 2 from the magnetic moment of corresponding classical object. It gives a so-called fine structure of atomic spectra that can't be understood in terms of the Schrödinger equation, and a bunch of other stuff. So all that. So I'm gonna pause there and see if there are any comments or questions.
Do they have homework? Is there homework in addition to these lecture questions?
Yes, the question from the floor, is there homework in addition to these lecture questions? Yes, there is. Let's go have a look at go look at some homework, shall we? Now I have to apologize for the appearance here, because it's, for those people in the room, this projector is somewhat non-optimal. Let me go see. Let me find a browser here. This looks like a browser. Coursera. By the way, this week there is no homework because there's a final exam, 2 3-hour parts. And I'm not going to show you the final exam questions because that's a case where the exam is timed, and so you know, I don't want to. Oh yeah. So for those of you who are interested, let me put this up on the. Let me share this with the Google Hangout people. First, I'd like to put on my costume. I am a professor, after all. Do you agree, Professor Copeland? So, let's see. Having accomplished that very important thing, screen share. This is the 3rd edition. We had like 37,000 people enrolled first time. The numbers dropped. You know, the fad factor grew out. Plus, maybe it's a lousy course. I don't know. This edition, there are like 14,000 people. So here is the. I'm looking at like the Inside Managers page right now. But here is if you had enrolled in this course, which I know you would never do. This is what you'd see as a student. And so here's the homeworks. So let's look at the homework that was given with this week 7 lecture that I just said. So the homeworks it's like there's no time limit. Well, there's a time limit of 2 weeks, but once you can start, you can look at the thing and then you can go away. You can come back a couple of days later. With the exam, it's more like a real exam. Okay, yeah, I'm going to agree with the honor code. Well, actually, so this is a problem which is sort of left over from the previous lecture. Actually, that was one of what you saw was the second of 2 lectures in week 7. The first was on angular momentum. There's 2 lectures per week. Each occupies about an hour and is cut into 4 or 5 parts of between 10 and 15 minutes. That's the format. All right. Okay, so who's going to answer this? Which of the following expressions correspond to quantities that have angular momentum of L equal to 3 in units of Planck's constant h bar? Who's feeling lucky? How about this? R is x1 squared plus x1, x2, x3 are the conventional Cartesian coordinates. R is the sum of the squares. How about R cubed? Does that have angular momentum of 3? The answer is either yes or no.
No, it doesn't have the right units. Do you care about units?
What do you mean? No. Does it have angular momentum of 3? When you operate it on it with the angular, it doesn't matter what the units are. Does it, when you operate on it, do you get an eigenvalue of 3? Well, this is spherically symmetric, so it has angular momentum of 0. This one has angular momentum of 1. This one has angular momentum of 1. Mr. Wong? Yes or no? Yes, that has angular momentum of 3. That has angular momentum of 3. Actually, what the students were taught in the previous example is that if you have a solution of Laplace's equation in polynomial form of degree n that satisfies Laplace's equation, then that is the answer is proportional to a spherical harmonic. Now this one, so the other previous question the other previous homework, the other previous lecture dealt with perturbation theory. And so it's used perturbation theory to calculate the effect of Earth's gravity on atoms in a harmonic trap. Okay, so here's the original Hamiltonian. It's a one-dimensional trap, just for simplicity. There's a harmonic oscillator potential. Here's some definition of the raising and lowering operators, stuff like that. Okay, and so this is like a multi-part question. It asks a question. So we're going to find the eigenfunctions of the original Hamiltonian that satisfies this equation, and it asks for the form of the eigenfunction. The one-dimensional oscillator says, you know, an exponential function has pure numbers in z. Which parameters of the Hamiltonian occur in the argument of that function in their simplest possible form? So this is just going to be solved by dimensional analysis. What are the dimensional units of that function? Now we include the effect of gravity by perturbation theory. So we have the standard. We have this additional potential mgz, which we add on to the original Hamiltonian, and then we solve the equations of perturbation theory order by order. So the first question is, compute the first order energy. The answer is this one, 0.
So is the other question not controlled?
Pardon me?
Is the other question not controlled? Are all the questions not controlled?
Well, this is, no, not all of them. Some are numerical answer, but most of them are, because it's graded by machine. So, so which of the following are true? Well, can anyone tell me why E1 is equal to 0? It's just by symmetry. It's just by symmetry. If you develop the equations, you get this. You have E1 is the expectation value of V over the ground state wave function that vanishes by symmetry. Okay, then you're required to compute psi1 and figure which of the following properties are true. So, you know, this one, the only way, some of these are symmetry properties, but others others need a little bit of insight. And now compute the second order energy, which involves, they had seen an example like that in the lectures. And the answer here is one of these. This one, I suppose. All right, so one of the things that was done in the previous example, in the other examples, was the polarizability of a rigid rotator, like a polar molecule, the polarizability of the hydrogen atom. One of those goes to infinity as h bar goes to 0. The other goes to 0 as h bar goes to 0. And so the question is, what happens to this, the E2, in the limit, in the classical limit? Well, it turns out the second order energy is independent of h bar. And now, here's the best part, I think. Having done all this work, all that work, now solve this problem exactly, not using perturbation theory. And I think I tell, you know, it's not like being mean, or not that mean. What you do is you just shift the coordinate so as to eliminate the linear term while introducing a constant. And so it turns out that the result calculated from second order perturbation theory is identical to the exact solution. So it provides an example of the type that I've been suggesting is important for a long while, which is when you can't do anything else, use perturbation theory. And when you can do something else, also use perturbation theory and see if what you can do or thought you can do makes sense. And here's a case, and I deal with a couple of others where perturbation theory is solvable in closed form and can be paired with an exact solution. The other case that I dealt with is the isotope shift in the spectrum of hydrogen. There, perturbation theory, it doesn't give the exact result, but it does give an important part of the exact result. And basically, for calculations of the isotope shifts of the hydrogenic isotopes, protium, deuterium, and tritium, the first order result, the first order shift is good enough, and it gives the, so that's a problem that where the exact solution can be found by using a reduced mass, but using the ratio of the electron mass to the nuclear mass as a small parameter in perturbation theory also gives the result which agrees to leading order with the exact one. Any other comments or questions? We could look at another homework.
What about the discussion forum?
The discussion forum is very active. I can't believe I actually done it. I mean, this is what I'd call sort of a positive comment. It says I didn't know anything about it, and now I feel like I'm almost done. And that's kind of nice. Then there's some other comments about how I snort and suck my teeth during lectures, but I don't think we need to look at that. And well, so like, okay, so you see these. Let's look by so-called top threads. So you know there are some discussions on entanglement that have a number of people posting, and hundreds of people viewing. Yeah, this homework 5, question 6. This one was a nightmare. Let's go look at that. Homework 5, question 6. Oh yeah, answers to some of these questions requires the use of Einstein's 1905 paper and Bohr's 1913 paper. In order to answer these questions, you had to read those papers. Google will not reveal the answers to these questions. I assure you of that. Here's So here's the one. You have to read the 1905 paper by Einstein, and a copy is provided to the students. What value does Einstein quote for Lenard's measurement of the largest effective wavelength for air? Express your answers in integer units of nanometers. This is the paper on the photoelectric effect. It's actually on 3 problems. If you've never looked at this paper, you've just missed life. The 3 problems are the photoelectric effect, Stokes' law of fluorescence, and the ionization of gases by ultraviolet radiation, which is my favorite subject of all. Both the photoelectric effect and the ionization of gases were experiments done by Lenard, who won the Nobel Prize, I think in the year 1905, or in the year 1904, I forget exactly which. And they showed the similar thing. The photoelectric effect showed that there was a frequency threshold for ejecting an electron from a metal. The ionization of gases by ultraviolet light also showed that there's a frequency threshold for the ionization of gases. And so that meant that it's discussed in terms of the wavelength, and what Lenard showed that if you have a wavelength longer, the answer is than 190 nanometers, it doesn't ionize air. But if the wavelength goes below 190 nanometers, it ionizes air. Then I asked about the Bohr problem. What was the one they couldn't stand? It was question 5. No, it was question 6. This one, to me, it's like the simplest possible problem of using a variational estimate of an eigenvalue. So it says, we're going to use the one-dimensional Gaussian wave function of this type. I've been beating him over the head with this wave function. Here's the relationship between the characteristic length of a harmonic oscillator and h bar and m omega. And so what we're going to, we have an equation. Okay, here's the general problem. Okay, we're going to use this equation to make an estimate of the ground state energy. Well, what we do is we take this trial wave function. We have a Hamiltonian. We take this expectation value. We call that E sub d, and then we minimize E sub d with respect to d. In other words, we find the value of the Gaussian width that minimizes the energy, and then we use that as a variational estimate. So I asked them to solve that problem where the potential is just the delta function potential. So in order to do that, I mean, you have to, what you have to do is evaluate these we have to evaluate the matrix element of H, which is T plus V. And so the matrix element, the kinetic energy operator, that's been, that's something you get just from the virial theorem for the harmonic oscillator, but it's a Gaussian integral that you can do. It's independent of the potentials. You can do once and for all. And then the expectation value of a delta function potential is just equal to the value of the wave function at the origin. So it's the simplest integral you can do, in my opinion. And then you here's the exact answer, and here's where they were asked to give a numerical value to 5 digits of accuracy. And many people found this problem to be intractable. Oh, here's another one, the Bohr model. Yeah, that's why I have people also, they have to read Bohr's paper to answer one of these questions. What is it? Oh, yeah. Yeah. Okay, I even give the page number. It's not like I'm a hard guy. Quantization of the angular momentum m. Bohr states that m must be the integral multiple of a fundamental quantity m0. By the way, he says what m0 is. He says it's Planck's constant divided by 2 pi. Then he gives a numerical value. But Bohr, not having been a camp qualifier, doesn't specify the units. Well, earlier in the paper, he says something about we're using the conventional units. He gives a numerical answer. He gives a numerical value in his paper. So my question is, how much does his number differ from the presently accepted value of that quantity? And by the way, in the course material it said, whenever fundamental constants are involved, you're to use the following as a reference. It's the NIST reference database on fundamental constants. Well, one of the students said that they spent 7 hours on this problem, and they, here's the 3 choices. Bohr's value is greater than the present value by about 10%, less than the present value by about 1%, seems to differ from the present value by a factor of 2 pi. That's a little joke about Planck's constant versus h over 2 pi. And this person who worked on it for 7 hours said, none of those answers is right. Bohr's answer is wrong by 7 orders of magnitude. They posted that on the discussion forum, and here's the value of the discussion forum. I just waited for someone to say this, and they said, that's the conversion factor between ergs and joules. Think again. Reply, oh, I got it. This is a proxy for real life. You read these papers, they seem to be full of bullshit that you can't understand. There's no manual when you read an original paper. But I was going to say something else. Oh, yeah, the Bohr model. The Bohr model is, like I tell them, use it for everything because it's so easy. It doesn't take any time, and you usually get sensible answers. So this is the Bohr model for a bouncing ball in the Earth's gravitational field, a problem we later look at from the standpoint of quantum mechanics with reference to recent experiments in neutron interferometry. But I say, look, let's just do the Bohr model. So use this Hamiltonian. It's just p squared over 2n plus, here's this, we're just saying, we're making a radial potential. It's a uniform radial acceleration. I made the big mistake of saying that this is a model that's a good approximation to the motion of a particle near the surface of the Earth. Gravitational acceleration constant. So this is like the Earth's gravity. This caused more trouble. This, what I thought was a harmless observation, people said, well, my answer depends upon the radius of the Earth. The radius of the Earth is nowhere here. And so I think I just say, how do you do it? Okay, determine the circular orbit. And this is the Bohr postulate. Bohr says, he says, oh, we've got this theory that explains a hydrogen spectrum. Is there a simple interpretation? He says, yeah. It's like these orbits that I've said are the ones that are going to be stationary. I had some energetic arguments, but in fact it turns out that the choice of orbits means you choose orbits where the orbital angular momentum is an integral multiple of Planck's constant divided by 2 pi. So you just do that. And so I said, okay, now we've got, what do we got? We've got m and we've got f, and then the momentum contains a factor h bar. So find the characteristic energy scale, which is just made up of the constants that appear in the problem. This is, it's one of these things. Then, using the value of epsilon, state the value of E1. Using the characteristic energy, state the value of the lowest eigenvalue in units of E1. It's got to be a pure number. Well, here's another person said, I spent hours on this problem, and I just don't get it all. I can't, the energy doesn't work, the energy is not proportional to any of the things that you put in this part of the question. So contrary to my practice, I said, okay, send me a summary and I'll look at it. Because, you know, I might have made a mistake. So he sent me a summary. He said, okay, now here I insert the Bohr radius. Okay, so because I used the name Bohr, he figured the Bohr radius A0 was in this problem. It has, you know, nothing whatever to do with it. It has the, you know, it has the electron charge and the electron mass in it. There's no such thing in here. And then the final thing, how do the energies scale with n? And it turns out they just are just proportional to this scale constant times n to the nu. So what would you call that? A geometrical sequence. And it turns out that the value of nu that you get does describe the order. It's the same that you get from quantum mechanics solving the problem for bouncing ball with Schrödinger equation.
Now, these are students who have no previous experience with quantum mechanics. Do they have any previous?
Well, no. I mean, there's no control over who's a student. We say that this course is set at the level, sort of around the level of the advanced undergraduate course in quantum mechanics or the beginning graduate level course as taught at the University of Maryland, quantum mechanics, which is, I mean, we make that very clear. We say the mathematical background is needed, and we give them up. We don't give them an entrance quiz in math. We have a document that says, here's some of the stuff that's going to be used. You know, multivariate calculus is required. Some people come in and they can't do the calculus and leave. Others seem to learn as they go along. May not have a background in mathematics or physics. I'd say the majority of our students are people who have gone through university in one way or another. They're often engineers, or I mean even people with arts degrees who, you know, they're not in the same demographic as university students. We've got a pair of 13-year-old twins from Pakistan who are taking this course right now. I wish them well. One of them was profiled in, so as of a year ago, these massively open online courses were a big fad. And your favorite man, Thomas Friedman, the columnist for the New York Times, was writing these columns saying it's going to transform education. And one of the people that he interviewed was was one of the twins, then 12-year-old girl from Pakistan. Her twin brother. The two of them are taking this course. And actually, the first edition, Victor Galitsky was looking at the forums. He's my co-author on this. Victor Galitsky was looking at the forums. He said, "Oh, I've got that girl from Pakistan. Boy, she has a platform, and she's complaining about the sound and all the subject material and everything." So another student, told me that the two of these twins were taking the course again this time. Well, but one of the first comments posted on the forum was, well, my sister and I started this course a year ago, but we didn't understand a thing. We hadn't had calculus. We took calculus, we took advanced calculus, we've just completed a course in functional analysis. They're 13-year-old kids. And we're looking forward to this course. And they're, the comments they're making this time are, well informed and constructive. So there's all kinds of stories. Yeah, I'm gonna shut up in a moment, but I can't do that before I just mentioned a little anecdote about this Einstein paper. So, okay, like I give the students a copy of the Einstein paper. the photoelectric effect. Actually, I give them several things, okay? One is this incredibly wonderful book by Lanchos, who was the personal assistant to Albert Einstein for a while. Lanchos wrote this book, and half of it consists of Lanchos' summary of each of about 20 of Einstein's papers, the ones published between 1905 and 1917. They're the best things ever written. They're very brief, but they tell you what Einstein did. Let me see. Where does I quote? Here's what Lanchos says in his original. Said, look at it. Although I offer occasional difficulties to the reader, blah 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 blah. Something appeared completely clear to Einstein does not appear to be so to the reader. Yeah, but I mean this book, which you can find on the free on the internet, contains these summaries. So I extract the one on the photoelectric effect. They're really good. And so this document also includes the original paper in German of Einstein and a link to an English translation. So after I wrote this homework problem because it involved ultraviolet light. And but before publishing the homework, I thought, well, I'd only looked at the German. I can read German good enough to make out what Einstein is saying. You know, good enough to know that he's saying 190. He puts it in centimeters. I know how to convert to. I go for the centimeters to centimeters. Okay. I read it. I can read it well enough to make sense of it like that. But I hadn't looked at this English translation that I linked to. I'd better look at the English translation and see what it says there, because nobody reads German. Well, the English translation is on this wiki source. You know, it's a document that anybody can edit. And the passage that was there in Einstein's paper was just gobbledygook. It's as if it had been produced by an optical character recognition thing and had just encountered a word stream that it couldn't recognize. So someone reading the English translation that was available on this wiki source would have no idea what the answer was. Okay, well, I know how to edit wiki documents, but I had noticed that a German-speaking student forum had spontaneously organized itself on the discussion forums. So I wrote a message to the German students forum, and I said, look, here's this thing. It's probably the most widely accessible English translation of Einstein's paper. It's got a mistake in it. You know, I assume that your command of English is better than my command of German. Why doesn't one of you fix it? I sent that off before going to bed one night. I got up in the morning. I got a response from one of the German-speaking students who had gone and made that translation correct. Later, a couple of weeks later, I had another one of these reading assignments from Einstein. Actually, it's a pretty good. I was going to shut up. You have to see this thing that I come up with. Actually, it's what Einstein came up with. I think this must be in week 5. Is that be right? Or were we just on week 5? Oh yeah. Subtle point to Einstein's paper. Einstein goes in this photoelectric effect. We were talking about this at lunch today. But he says this only applies when there are relatively few quanta of light present.
Oh, yes.
These no longer apply when the number of energy quanta per unit of volume that are simultaneously involved in the transformation is so large that the energy quantum of the generated light can receive the energy of several exciting energy quanta. That's a prediction of multiphoton processes, which no one had ever seen at the time that paper was written, which were made only possible by the invention of the laser that Einstein predicted in 1917. Okay, now, talk about your one-stop shopping store. So this question actually just says, it gives this thing, okay, if we take, we have these three reference lasers that are used in the course. 650 nanometers, Balmer alpha. 532, the famous green laser. 4 or 5 nanometer Blu-ray laser. And so the students are asked to answer the question, how many photons for each of these lasers does it take to ionize the atom? Well, there's someone who said, I've spent nearly 2 days on this problem. I give up. But in this case, I'd read the German thing again. I was writing this problem. I thought, oh, God damn it. I'd better go look at the English translation again and see what it says about, in this passage. And once again, this time it wasn't nonsense, but it was garbled up so that no one could tell what it said. So I wrote this student in Germany again. I said, this time I addressed him in German. I said, it seems to be another problem at such and such a place in the paper. I think the solution to it is this phrase, but would you look into it? Let me know what you think. So within hours, I'd gotten back the message that he'd gone and fixed it, and then he said, when this course stops, I'm going to spend a lot of time cleaning up that English translation of Einstein's.
Service to the.
Well, it's better than nothing. A lot better than nothing.
Well, it seems to me that the course is a little eccentric.
Let me put it to you this way.
Yeah.
It's more than a little, but it has to fit into lectures of 10 minutes. Why?
Attention span.
Exactly. So yes, I mean, I introduced perturbation theory as in part of a 1-hour lecture, and I use it to solve a number of problems. Okay. So then it's in the pursuit of the homework that people actually get the opportunity to apply it. And the homework problems tend to be pretty much real problems rather than contrived examples.
But I would say that they're real problems from the view of an expert. And so perhaps that's as it should be, but I could see why students would have difficulty having gone through maybe a much more conventional hold your hand type course, which is normally what's given around here.
Well, such courses are of great value. That's how most people are going to learn quantum again. But if you really want to be able to solve problems, you have to solve problems. So the lectures, I think, are, basically only kind of introductions to, well, they're basically illustrations of what people have to do to get through the homework and the final exam.
I think people with advanced quantum mechanics knowledge would find this very, very informative and I guess illuminating, because you bring in sort of a wide variety of phenomena from a kind of sort of simple viewpoint. But that's only when you really understand it in depth, and so that's not so accessible to less experienced people.
Right. Well, I'll just say, I think you're correct, and I don't think that I'm the right person to teach, you know, sort of a Physics 101 course or an elementary modern physics course. I'm not persuaded that my own skill set is ideally matched to that, and and I'm not sure that that's the best use of my time. I mean, you know, I spend these weeks in Camp Qualifier dealing with qualifier exam level questions, and the students are told up front some of these examples we use here are comparable, you've actually taken from the polarizability of the polar molecule is one that I took from a University of Maryland qualifier exam course. So if you take this course, you're going to get exposure to that material. Now, you know, if you haven't the mathematical background, you haven't got the, you know, something that just talks about like the famous equations and has pictures of people and doesn't require anything. I mean, it doesn't require effort is fine. I mean, you know, I read novels. Okay, I don't have to like. Not everything I do with my mind is hard, but quantum mechanics is hard. So there's lots of popular books on, you know, quantum computing and all that. There's plenty of soft literature available, and then there's stuff like Wikipedia. So I mean, there's a vast range of offerings, and I think Victor and I have the attitude we're going to teach people something that resembles, you know, graduate level quantum mechanics. And, you know, if that doesn't attract the 160,000 students that Andrew Ng's course in machine learning attracts, so be it.
Well, I think you provided an important service, and the students who do make it through will really not only have learned, but kind of get a sort of philosophy of how to treat these things. And, carry it with them.
What are the completion rates?
Oh, yeah, that's a good question. What's the completion rate? So we have these like tens of thousands.
Yeah.
The simple answer is it's about 5%.
Okay.
But
that's a universal number.
It turns out that our completion rate is about the same as the average completion rate of any of the Coursera courses. They all are somewhere between 3 and 5%. Mm-hmm. So there's another more important metric. I'll say it this way. I've looked at the statistics. Like 37,000 people signed up for the first edition. Of those, about half, 18,000, never did anything else. They signed up, then when they got the email, the courses started, they had better things to do. So they never looked at a video. They never engaged with the course at all. Because to get, you know, to view these things, you have to sign up. You just have to give them an email address. That's all. There's no other information required. But then it tracks students. You have to log in with your email address. So half of those people never even logged in once. Okay, then that leaves about 18,000. Then of those, 9,000 people left after viewing the first video and never came back. So we had an attrition rate of 75%. Half never came. The others came maybe even for a few seconds and said, no more of this. But then for those who stay through the third or fourth week of the 8-week course, they tend to be invested. So the completion rates are, I don't know exactly, but there may be like 30 or 40% of those who find themselves invested. And the funny thing is, these numbers are very similar for all the Coursera data that I've seen. I've seen quite a bit of it. For, you know, there are these courses like there's a guy here who's teaching like the most brilliant course imaginable, how to design an Android app. Android, for example, is the operating system that powers these. This is a mobile phone. And this guy, Adam Groh, professor of computer science here at Maryland, has 200,000 students enrolled. And the final project is the construction of an Android app, which will then be peer graded by the students in the course. So the students themselves will vote up what they think is the best completed student project. And he got an agreement from Google to feature the top 5 student apps on the Google Play Store. Now that's a course worth taking. I mean, you could build an app that would be featured by Google on its store.
Well, I think it is.
So I don't know what the completion rate for that is. So that that's something where there's the outcome is of a very potent and let's say testable variety. The test of an app is, does it sell like hotcakes? If it doesn't, it's crap. So
but there is this universal constant, which is the lecture number times the number of students attending is a constant. So by the time you get to lecture 10, you have 1/10.
Yeah, but they're all back by lecture 11. They can't afford to leave.
You'll have to excuse me.
I'm done. Okay, any final questions?
But this is still a lot of people, right? Even if it's 5%.
If not, I'm going to bid you all goodbye and hope everyone has a great weekend.